Okay, so guys, once again, the only things that you really need in your possession are this, and we'll talk more about this when it becomes important. Because you're going to need this table, and then you're going to need this guy, which you're going to find out very shortly is a battery. So guys, this is fascinating, but it is also the stuff that they love to test you on when it comes to electrochemistry. Because in this one topic, they can ask you questions about precipitation, they can ask you questions about half reactions, they can ask you questions about spontaneity, they can ask you questions about Gibbs free energy. We'll make those connections on Thursday. Guys, they can ask all sorts of different questions just by talking batteries with you. Now, guys, before we get into this conversation, and I really think this is it's fun. This is neat stuff to think about. But guys, before we get into this conversation, we are coming at this from a bunch of different angles. Some of you have taken physics. Some of you haven't. Some of you, based on science classes that you took in the past, you understand some things about household current. You understand the difference between AC and DC power. You understand the difference between voltage, amperage, and wattage. Guys, if those things are not true for you, we're going to have a free-form conversation. There are no notes about this. We are going to have a free-form conversation about the things that you need to understand about electricity. I'm just going to be scribbling on the board as we run into interesting ideas. Some of you know more about this than I do. That's great. Some of you know nothing. That's not okay. But guys, all of you have got to have at least a foundational understanding, if nothing else, in what voltage means. But guys, it's helpful to understand voltage as it applies to amperage, as it applies to wattage, if for no other reason than because someday you're going to buy a house and you're going to open up that big gray panel and you're going to be faced with a bunch of circuit breakers and you're going to have no clue what those numbers mean. Let's talk. So, guys, with all of that said, the things that we need to keep track of are these. Voltage, amperage, which we're just going to call amps, and we're going to call this watts. Well, this is watts. So guys, what I'm going to do is I'm going to explain these concepts to you by using the concept of water flowing through a garden hose. And guys, understand that this analogy is so good that and understand I have no background as an electrician. And I am not an electrical engineer. I spent 2 years as a mechanical engineer. But guys, I will tell you this. I've rewired my house. When I finished my basement in my old house, I did all the electrical wiring. Last weekend, I broke into the main service disconnect on the side of my house and wired a 30 amp 110 plug for the new camper trailer that I just bought. Guys, and the only reason that I know how to do all of that stuff is because I think of electricity as water flowing through a hose. So guys, understand that this isn't the way electricians think about this stuff, but it works really well if you understand it. So with this idea and by the way, I'm not telling you should go dig around in your service panels, but this does work. So guys, it goes like this. Thinking about water flowing through a pipe, voltage is like pressure. Amperage is like flow rate, which in this case would be measured in something like gallons per second. Gallons, well, probably not seconds. That's a lot of water. Probably more like gallons per minute. And then, guys, wattage, for those of you that are cyclists, you know that power meters on bicycles measure wattage. And this is all about power. So imagine that you're using a garden hose to spray the dirt off your driveway. So guys, the analogy then goes like this. Hose. So guys, when water comes out of a garden hose, this can work in a lot of different ways, right? So if you've got a garden hose hooked up to what's called your hose bib, that's what that thing is called on the side of your house. It's called a hose bib. You hook that thing up to your hose bib and you turn it on and you allow the water to flow out of the hose. And what's it look like? Yeah, you just got water, it's kind of coming out like this and it just falls to the ground, right? So guys, talk with me about pressure. If the water is simply flowing through an open garden hose, is the pressure high or low? It's very low, right? That water just sort of, and it just, you can picture it, right? You're standing garden hose, right? But at the same time, what about the flow rate? Pretty high. If you want to fill a bucket with water, guys, you don't stick your thumb over it, right? If you want to fill a bucket with water, we're concerned about flow rate. We want as much water to come out of that hose as we possibly can. So you don't stick your thumb over the tip. You just allow that water to flow because we've got a very high flow rate, which allows us to then fill up the bucket quickly. So in that state, we've got low pressure, we've got low voltage, but we've got a high flow rate. Do you see how those things relate? Okay, but now guys, what about this? Imagine that we then want to extend the stream of water and cause it to fall or fly longer, like we want to project the water further out into the yard or whatever. So what do? Well, you either get a nozzle and screw it on there, right, a spray head, or you can simply stick your thumb over the end. And guys, when you stick your thumb over the end, what's the experience that you have on your thumb? You can feel the water push, right? Because that's pressure. What you're doing is you're increasing the pressure on the water. You're increasing the voltage. But as you do, what happens to the amount of water flowing out of the hose? It goes down. By the way, guys, if you want to take this analogy and drive it further into this, it actually works. Your thumb is offering resistance. Resistance causes voltage to go up. That's Ohm's law. You can learn about it later if you want to be an electrical engineer. But this analogy actually works even better the deeper you get into it. But the idea, guys, is if you stick your thumb on the end of the hose, you are actually increasing the voltage. You're increasing the pressure. That water is now moving with greater force. Notice, however, that you're dropping the amperage because not as much water comes out. And if you wanted to use that hose to fill a bucket, it's going to take longer because less water gallons per minute is coming out. You get the idea? Okay, now, what if you want to clean your driveway with this hose? Well, guys, there's a couple different ways you can do it. One of the things you can do is you can stick your finger on the end of the hose and you can use this water to blast the dirt off your driveway, right? But there's actually another way you can do it. You can actually take your thumb off and allow all that water to wash away the dirt. And guys, it turns out that either one of those technically is equally effective at providing power and doing work. So if you have a high voltage, low amperage situation, that's your finger over the end, you can do some work. And we measure that as power, cleaning ability, watts. Those are our units for power in electrical world. Or you can come at it from another direction. You can go low pressure. Leave your finger off the end. But guys, you can use all that water to wash the dirt off your driveway. And either one is capable of doing equal amounts of work. But guys, work, so watts is actually voltage times amperage. So you can have lots of pressure. When you do, you're going to have low amperage, and that gets work done. You can also have low pressure, an open hose. You're going to have a greater flow rate, and that's also able to do a similar amount of work because the bringing together of pressure and flow rate is all about watts or power or the ability to do work. Does that make sense? So, guys, which one is a taser? Why do tasers light up criminals but not kill them? Guys, tasers are frighteningly high voltage, tens tens of thousands of volts. Guys, that's what pushes the current through the human body. But in order for that to not kill you, what do they have to do to amps? Got to drop it way down. If you're pushing electricity really hard through somebody's body, and if the amperage gets high, now you're pushing a lot of water, a lot of electrons. And you guys understand that, right? Electricity is a flow of electrons. Guys, if you're pushing high amps with high volts, that equals dead. So if we want this balance, like in the example of a taser, we're really high voltage but really low amperage, and consequently you don't end up dead. So guys, what about the starting battery in your car? How many volts is your battery in your car? 12 volts, really low voltage. But guys, what's the amperage? Do you guys know? Typically between 500 and 700 amps. Because guys, what you're trying to do is you're trying to spin this big old motor to get your car to start. And so to do that, we go low voltage, but really high amperage. And it's like a flood of water pushing the starter motor that causes your engine to turn over. But guys, have you ever touched the contacts on a car battery? Why don't you die? Because there isn't enough voltage to push all of that current through your body. So guys, understand that it's the bringing together of those two things that's trouble. So guys, do you understand sort of the foundational stuff about this? You okay? Okay, so now let's tease these two ideas apart really quickly. Guys, there's two kinds of electricity in this world, DC and AC current. Do you understand the differences? Do you? Let's talk about it quickly. Guys, where do you find DC current? Batteries. Where do you find AC current? Outlets in your house. Guys, the electricity that is flowing through your home receptacles or your lights or even here in the school. Guys, it's not the same electricity as the electricity that you get out of batteries. And guys, interestingly, I don't know if you know about this tension. Back in the early 1900s when we were electrifying the company, did you know that Thomas Edison was actually fighting to get every city in the nation to be wired DC? Thankfully, Nicholas Volta came back and said, you're an idiot. We need to be on an AC current grid. Guys, if Edison had won, we would have never developed as a nation because DC current is wildly inefficient when it comes to mass transmissions of electrical power. So guys, so maybe you don't know this. DC stands for direct current. AC stands for alternating current. So guys, what's the difference? And fundamentally, it's this. So guys, when we talk about DC current, and the reason that we're talking about this is what we're going to do today. We are only going to talk DC current in this class. Guys, when you think DC current, think about a battery. And it's got a positive end and a negative end. This is what is called direct current. Now guys, which direction does this current flow? Positive to negative or negative to positive? Negative to positive. Guys, current always flows in DC systems from negative to positive. Does that make sense? What is electricity made of? Electrons. What's the charge of electrons? Negative. Where are you going to find more electrons? At the negative pole. So guys, DC current is directional and it always flows from negative to positive. So in order for DC current to flow, that current has got to flow from the negative pole back to the positive pole from where it came. So guys, contrast that with AC current. Guys, AC current does not come from batteries. Where does AC current come from? Electrical generators. So guys, maybe if you're tracking with this is battery current. This is generator current. This is the stuff that we find in our homes. So guys, how do we create batteries? We're going to talk about that in a minute. How do we bring chemical systems together to form these neat environments where we end up with electrons that are ready to flow with pressure? And we're going to talk about that in a minute. But guys, just so you're aware, I mean, you may as well understand all of this. Guys, how is it with AC current? How do we create electrons that are ready to flow with pressure, voltage? Do you guys know how we do this? We take a magnetic field and we spin copper loops of copper wire inside a magnetic field. Guys, there's this phenomenon in our universe, in physics, that says if you take a wire and if you spin it in a magnetic field, as that wire spins in the magnetic field pushes the electrons in the wire and creates a current. But guys, the trick here is that as you're spinning, imagine you've got a wire that's surrounded by a magnetic field. As that wire is spinning, you actually end up with the wire here being oriented in one direction in the magnetic field. The magnets don't move. When it spins 180 degrees, now it's oriented the other direction in the magnetic field. And as that wire alternates, it actually alternates the direction that the current is flowing. And so you actually end up with a current that is alternating direction of flow 60 times a second. So guys, I don't know if you know this or not. Do you know that every single light bulb in your house is flashing on and off 60 times a second?
Have you ever taken a slow motion video?
Mm-hmm. Yeah, that's why. Guys, and you can actually do this if you're interested. Take a piece of paper and make a circle out of it. And actually, cardboard works better. Take a piece of paper, or cardboard, make a circle out of it. Put it on the end of a pencil or something like this so you can make it spin. Then cut a slit in it that you can see through. And if you spin that at 60 times a second looking at a light, the light will go out. Because you're actually shielding your eye from the light at exactly the same rate that light is flashing on and off. And guys, every single light in your house, except for LEDs, flickers 60 times a second, because that energy is switching from positive to negative, is switching back and forth 60 times a second. Yeah. Yeah. It's not hard. I mean, I've done it. It's not impossible. Yeah, it's not as hard as you would think. It's yeah. Well, and this is where things get interesting. Instead of thinking of the electricity flowing this way, which is actually not bad relative to our hose analogy, what we actually see is, you've taken trig, at least, you know about sine waves. It turns out that our electricity is actually sinusoidal. And so it's described by a sine wave where the poles of the current are flipping 60 times a second. So really, to think about it, because it gets into the physics of electromagnetics, it's actually cycling from positive to negative 60 times a second. Guys, understand, in Europe, they don't use 60 hertz electricity. Oh, did you hear that word? Hertz, right? Things per second. Guys, our electricity is 60 hertz electricity. In Europe, they're on a different standard. And so you can't plug US stuff in Europe, because our electronics and things are looking for 60 hertz electricity. In Europe, they don't use 60 hertz electricity. They also don't use 110 volt electricity. Over there, everything's 220. So it's kind of a mess. But anyway, so the other thing is this, guys. When the electricity leaves our generators, the electricity does not go back to the generator. Where does it go? It goes into the ground. if you look on the side of your house, you will actually see literally a metal rod next to your power box driven into the ground with a green wire that goes to it. You guys understand that rod is not where your electricity should go. That electricity is a fail-safe if your house gets hit by lightning or if there's a short in your system. That is your fail-safe path to ground. But guys, understand that what we do is we feed all of our used up electricity back into the grid, and the power company sends all of that electricity literally into the earth, into the ground. It doesn't return to the generator, it goes into the ground. So literally it goes into the ground. So AC, DC batteries, you guys good? Yeah. Perceive the flickering. I know that there are cases of people that are very susceptible to seizure disorders, where sometimes the flickering of these lights can, even though they can't perceive their flickering, subconsciously they do, and it can trigger seizures. But I've never had the experience of being able, other than with the spinny thing, or like you said, shoot a video, and if they're out of sync, sometimes you can see them flicker. I've never been able to perceive with my eye. Chances are good if you see flickering with your eye, it's because at the point of generation, there was a glitch in the generation process, and there was a moment where you weren't receiving power. So that's possible. So, yeah, Doug.
Are like magnets and stuff affected by the magnetic fields of AC current?
Yeah, so it goes both ways. So a motor is just a generator in the opposite direction. I'm not sure if this is what you mean, but if you take a magnetic field, spin a coil of wire in it, you get power. You get electricity. All an electric motor is the opposite of that. Then what we do is we have a magnetic field, and now we pass electricity through a coil of wire, and now that coil of wire is pushing on those magnets, and it makes the motor spin. So literally, if you take an electric, just a little rinky-dink stupid electric motor, like out of a fan, a cooling fan for a computer or something, and if you hook a voltmeter up to it and spin it, it makes a voltage. Yeah, it's exactly the same process backwards. So, you guys good? Good? It's interesting, right? All this stuff. It's, yeah. So, all right. So, guys, what are we going to do with this? Well, understand that where we are headed is right here. We're going to now we're not talking about AC current. We're not talking about electrical generation at power stations. We are talking about how to make batteries. How do we bring elements and compounds together in such a way that we can get them to create current? And guys, you ready for the 30-second overview? Here's how you do it. You get one element that really wants to give away electrons. You get another element that really wants to take in electrons, and then you separate them. And one of these elements is giving away electrons, one of these elements want to take in electrons, and then you connect them with a wire. And when you connect them with a wire, the element that wants to give away electrons shoves the electrons into the wire, and then the other element goes, hey, electrons, come over here, I'll take you. And you've got one pushing, and you've got one pulling, and that creates a pressure that we call voltage, and that's what causes the current to flow. That's the 90-second overview. Do you understand the idea? One element pushes, one element pulls. The pushing and pulling creates pressure that we call voltage, and that's what creates what we call a battery. You guys good? Okay, so guys, how do we think about this? Well, this is the idea. Digging now into our notes, we talked about all of this idea of voltage, pressure, high-low. Okay, so guys, this then is how this goes. Hi, how you doing? Yes, please. So, guys, we've got these ideas, right? That oxidation is the losing of electrons. You can picture a metal losing electrons. Off they go. The metal becomes positive. Guys, what you're going to find is that in the case of a battery, what you're going to experience is you're going to have an elemental metal. And when that elemental metal is oxidized, it loses electrons. And as it loses electrons, it becomes an ion that dissolves in water. Then reduction is the gaining of electrons. Electrons are on the reactant side. Typically relative to batteries, what we're going to see here is an ion with a metal ion in solution floating around in solution. That positive metal ion grabs electrons, its charge is reduced, and it becomes the element, the solid metal that then gets plated onto an electrode. So guys, with that as a background, I want to show you this from multiple directions. So we're going to take a look at this reaction. Guys, scratch it down with me. Zinc plus copper 2 sulfate yields zinc sulfate and copper metal. You got it? Step number 1, write the net ionic equation. Do it now. And guys, I'll do these with you in a minute. But given what we did last time, this should be well within your skill set. So we're going to write the net ionic equation. Then, guys, please write the half reactions and figure out which substance is oxidized and which substance is reduced. Yeah. It should be this, no, well, from the net ionic, but we'll talk about why in a second if it's not apparent. By the way, guys, we may run a couple minutes over today. I just gave you guys all eyes for pride. Okay, so guys, you should be done. So write the net ionic equation. Done? Is that okay? So the net ionic equation is the reaction minus the spectators. Sulfate is aqueous on both sides. It's not doing any chemistry. It's just hanging out watching. So when copper is bonded to sulfate, it's in a +2 state. When zinc is bonded into sulfate, it's in a +2 state. So guys, the net ionic equation then is elemental zinc plus copper ion yields zinc ion plus elemental copper. So now we can figure out our half reactions. So what is happening to the zinc? Is the zinc metal gaining or losing electrons? The zinc metal is losing electrons because it's going from an oxidation state of 0 to an oxidation state of +2. So this then is one of our half reactions as the zinc metal loses electrons. Now, is that oxidation or reduction? Oxidation, because the zinc metal is losing electrons. So now, guys, our other half reaction is copper 2+, and that copper 2+ is gaining electrons, and those electrons are taking copper 2+ ion and reducing. See how that just fits into the conversation? And that copper 2+ ion is being reduced to elemental copper. So have we satisfied all three of these? Is that okay? Okay. So guys, the question then becomes this. What does this look like? When zinc and copper 2 sulfate come together, what does this look like? So guys, what does this look like? It's a chunk of metal, right? You've probably only seen it as those little fuzzy pieces of zinc that last year we hucked in hydrochloric acid to make hydrogen gas. So guys, copper 2 sulfate, you actually need to know what this looks like. It's obviously a solution. What's it look like? It's clear and blue. Yeah? Not colorless, it's clear, you can see through it, but it's blue. Copper solutions are blue. Then guys, what does this look like? A penny. And then zinc sulfate solution, they wouldn't ask you this, but it's colorless. So guys, zinc sulfate solution is clear and colorless. So guys, with that as a background, see if this reinforces what you were thinking.
First, in an aqueous solution of copper sulfate, a similar oxidation reduction reaction.
So guys, notice what we've got. This is our reaction. We've got zinc solid, copper ion, zinc ion, copper solid. So guys, let's take a look at how this happens through animation.
When a zinc rod is immersed in an aqueous solution of copper sulfate, a similar oxidation reduction reaction
By the way, similar in that this is a clip of a larger video.
occurs.
So guys, this is what it looks like, if you will, at the atomic level. What are these things? Zinc atoms. What's surrounding them over here? Copper sulfate solution. Notice it has a little bit of a blue tint.
In this reaction, zinc is again oxidized.
So guys, what's that green guy? Copper ion. So copper ion is going to collide with the surface of the zinc.
Now, however, copper 2 plus
When it does, guys, this copper 2 ion has a greater affinity for electrons than the zinc atoms. And so the copper 2 ion steals electrons from the zinc. How many? 2.
ion is reduced to copper metal.
When that happens, the zinc ion is the copper ion is reduced to copper metal, but the zinc ion loses electrons. Its charge is now positive. It gets displaced from the metal and cast off into solution. Does that make sense? Now guys, here's the trick.
In this reaction, zinc is again oxidized. Now, however, copper
Okay, so you see the electrons starting to go. Guys, when does that electron get transferred between the zinc and the copper ion? What has to happen? Contact. They have to run into each other. Guys, the problem is this. These electrons moving from one place to the other, that's electricity. That's a current. The problem is that we can't leverage that transfer of electricity, electrons current, because they're happening through contact. And because they're happening through contact, we can't stick a motor or a cell phone or a Tesla or whatever. We can't stick something in between there and make that flow of electricity do work. So what do we have to do? Tease them apart. And when we tease them apart, we can then cause that simple exchange of electrons to happen through a wire. And when they do, we can stick something in that wire, like a motor or a watch or a phone or a light bulb or whatever else, and we can get that flow of electrons to do useful work. And guys, that's all a battery is.
2 plus ion is reduced to copper metal. In the two examples we have seen, zinc is oxidized because it causes the reaction to produce plus 2 ion are oxidizing agents towards zinc.
Okay, so guys, you get the idea about how this flow of electrons happens? So how do we turn it into a battery? And the answer is this.
When a strip of zinc metal is immersed in an aqueous copper tube.
So guys, you see it. So we've got the zinc metal, we've got the copper solution. The only difference is I think this might be nitrate, but why doesn't it matter? Spectator.
sulfate solution.
Oh, it is sulfate.
Electrons are transferred from zinc to the copper 2 ions. Copper metal deposits on the zinc strip and collects at the bottom of the flask.
So guys, look at the difference. What's on the piece of zinc? Copper. What do you notice about the solution? Less blue. Why? Copper's not dissolved anymore. It's the copper ion that's making it blue. So now let's turn it into a battery.
Zinc atoms are oxidized to zinc 2 ions, which enter the solution. This spontaneous oxidation-reduction reaction is summarized in the chemical equation shown. The spontaneous copper-zinc oxidation-reduction
Oh, sorry guys. I forget I can't
unit
do
in a
that. So guys, now we've got them separated. We've still got our piece of zinc. We still have our copper solution. But now they're separated. They're in different cells. Now it's a battery.
Oxidation-reduction reaction can be made to yield useful electrical work by incorporating it in a Voltaic cell. The zinc electrode is immersed in a solution of zinc sulfate. The copper electrode is immersed in a solution of copper 2 sulfate. No current flows through the light bulb because the electrical circuit is not complete. To complete the electrical circuit, we add a tubular bridge filled with aqueous sodium sulfate solution with a porous plug on each end. We now have a complete circuit and current flows. When we replace the light bulb with a voltmeter, we find that the cell has a potential or voltage of 1.1 volts.
What is that analogous to for us? Pressure.
The copper electrode is the positive electrode, and the zinc electrode is the negative electrode. As the cell reaction proceeds, zinc atoms of the zinc electrode lose electrons and move into the solution as zinc ions. At the same time, copper 2 ions acquire electrons at the copper electrode and form copper metal. The reaction in the left-hand compartment is oxidation of zinc. The electrode at which oxidation occurs is called the anode. The reaction in the right-hand compartment is reduction of copper. The electrode at which reduction occurs is called the cathode. Electrons flow from the anode to the cathode through the external circuit. To maintain electrical neutrality in the two cell compartments, ions must move through the salt bridge. In summary, remember that in a Voltaic cell, the anode at which oxidation occurs is the negative electrode. The cathode at which reduction occurs is the positive electrode. Electrons flow through the external circuit from anode to cathode.
You got it? Let's talk. Guys, grab that paper. What we're going to do is we are going to take all the information that you need to know about batteries and we are going to condense it onto this piece of paper. You understand that this is a schematic of the animation that you just saw. So guys, we are going to base our conversation on the zinc copper battery that we just looked at. Do this, guys. The first thing that we've got to do is let's identify what is in each cell. So starting here, this is zinc and this is copper. Doesn't matter, but let's keep it the same as our drawing. So guys, if that's the case, what is in the solutions that are in those cells? What's over on the left? Zinc sulfate, but sulfate, let me, guys, I think I may know why this isn't working. It is my pen. No, but they're both the same. The problem is that there's this little replaceable nub, and they've worn down to the point. I was going to go grab one of Miss Call's, but here, okay. So, but I can do this. There we go. So, guys, one of our ions, so let's start again. Sulfate is a spectator. We're not going to include it because it's not doing chemistry. Then, guys, over here, we've got our copper. We've got our copper ion in solution there. You could maybe picture that as being blue. Now, guys, we established in the video that and this is how, I'll explain why in a minute, but let's just talk about this now. Guys, which direction did the current flow? Left to right or right to left? Left to right. So let's write that in as a fundamental common point. I'll explain how we know that in a minute, but let's just take it as true right now. Because guys, once we establish the direction of flow, all sorts of other things begin to fall into place. So what are those things? And guys, the first thought, this is how this comes together. So if the electrons are flowing this way, does that make this cell electron rich or electron deficient? Electron rich. And we are going to represent that by labeling that electrode, and that's the name of the piece of metal. We're going to label that electrode as negative, and consequently this one is then positive. So now that we know that that electrode is negative, understanding that this side is electron rich. Guys, here's what that means. That means that whatever's going on inside this cell is giving away electrons. Is that oxidation or reduction? Oxidation. So let's write that down. So guys, that makes that cell our oxidative cell, making this cell then, of course, our reduction cell. So, guys, if, so we've identified this as our oxidation cell. So now the next logical step goes like this. If this is our oxidation cell, is zinc metal losing electrons to become zinc ion? Or is zinc ion losing, because we've said it's loss, right? It's oxidation. Is zinc metal losing electrons to become zinc ion? Or is zinc ion losing electrons to become zinc metal? The first or the second? The first. So guys, the way we're going to represent that is this. The zinc metal is becoming zinc ion. When that happens, we have a flow of electrons that go up through the wire, across the circuit, and back to here. So as these electrons return to, as they come to this side, we now have these electrons over here. So guys, who's going to grab a hold of these electrons? The copper ion or the copper metal? The copper ion, and as they do, they will be reduced to copper metal. Does that make sense? Now let's write the half reactions. What is the half reaction that's happening on this side? We've got zinc metal that is being oxidized into zinc ion with the loss of 2 electrons. Over here, we have copper ion that is gaining electrons and becoming copper metal. Now, guys, once we've identified these realities, we can now name these cells. And we use the word cathode and anode. And guys, I'm just going to tell you that makes this side, I'm just going to write it here. That makes this side the anode, and that makes this side the cathode. How are you going to remember that? Vowels and consonants. Guys, oxidation and anode both begin with vowels. Reduction and cathode both begin with consonants. Yeah.
Also, the cathode has the T in it, which is like the plus.
Yeah, absolutely. However you choose to do that. But now, guys, a thought that I know that you can connect with, but you will see this question on the AP. You're going to see this question on the test. You're going to see this. So, guys, the question is this. relative to mass. We're talking mass now. As this battery does its battery thing, what happens to the mass of the zinc electrode? Does it get heavier or lighter? It gets lighter. So guys, the mass of this electrode literally decreases. If you weigh the electrode at the anode, it is actually decreasing in mass because zinc metal is going into solution. Conversely, what's happening to the mass of this electrode? It is increasing because zinc ion is reduced to zinc metal. And so here, the mass of the electrode is increasing. Will tell you which cell is the oxidation and the reduction by telling you the mass changes. In a battery that's created with zinc and copper, the mass of the zinc electrode goes up as well. In this case, it goes down. But the mass of the zinc electrode goes down as the battery discharges. That immediately tells you that that's the oxidation and therefore the anode. So sometimes they will communicate that information to you simply by telling you the mass changes that occur with the electrodes. So you need to understand that idea. Okay, so go ahead.
This is probably out of place, but like, is the difference between like batteries that last longer, like a AA versus a AAA battery, like how much mass the negative electrode has?
That's exactly right. Yeah, so, and I don't know if you understand this, but we can talk about it quickly. It doesn't matter if you have a AAA or a AA, or in this case, a C-cell battery. They all generate 1.5 volts. It's exactly the same chemistry in each one of these batteries. The difference is the amperage that they can produce. They all produce 1.5 volts because they contain the same guts. The difference is that these are able to generate greater current, greater amperage at that voltage simply because they literally have more guts. Yeah, absolutely. Yeah, that's exactly right. Go ahead, Doug. Oh, yeah.
So, in a battery like these right here,
Mm-hmm.
is it like this or is it?
No, if you, and your book offers pictures of these. If you were to cut one of these in half, you would see that they have electrodes and they have different cells, but they're wrapped together. And they're actually, we haven't talked about this yet. We haven't talked about the salt bridge. Inside these batteries, the salt bridge is actually paper or something like paper that physically separates the two cells, the two electrodes, but allows current to pass through, allows ions to pass through. So they're the same basic idea. They're just literally wrapped together differently. Go ahead. Well, some of them aren't. I mean, they're now creating batteries you can eat. The thing that makes some batteries really dangerous is some of them, like NiCad batteries, nickel cadmium batteries, the old school rechargeables, cadmium is horrible. It's so poisonous. Batteries like the battery in your car, actually the electrolyte is sulfuric acid. And that's obviously a problem. But it's fascinating stuff. Maybe we can watch the video after the AP test. They are actually now making batteries out of organic compounds. It's crazy. It's a David Pogue video. You can jam holes in these things and they don't care. You can cut them up into pieces and they don't explode. And you can actually eat them. David actually starts eating the pieces of them. Yeah, it's crazy stuff. Guys, little side note, and I mean this seriously. If I had this to do over again and I didn't choose to be a teacher, this is what I would spend my life doing. Building batteries. This is going to change the world, literally. Guys, you understand we don't have an energy crisis, right? We have an energy storage crisis. We can make enough electricity through renewables to power our planet forever. We don't have to burn oil and gas in order to make electricity. The problem is the sun doesn't shine all day and the wind doesn't blow all day, and we have a problem with storing power. We don't have a problem with making power. And guys, someday somebody's going to figure out a cheap, efficient, scalable way to build what they call grid level storage. A way to store enough electricity that we can have electricity at night, just like we do during the day. And guys, when that moment happens, so many of our world's problems are going to be solved. You want to talk about a way to take science and use it to make a difference and get filthy rich along the way? Work on batteries. It's fascinating stuff. So anyway, yeah.
So I thought this is like, I don't know, I'll just ask a question. So we have, in the original we have, zinc plus copper sulfate. Isn't like the only thing that makes them switch electrons is number one, them colliding, and number two, just like them being there, and like the other's presence, whereas like here they're separated.
Yeah, that's a good question. That's a good question, and the answer is no. And we're going to talk about that when we get to this in just a minute. I don't ride this horse into the sunset, but it has a lot to do with electronegativity. We're comfortable with this idea that some species just have a natural attraction for electrons. Similarly, some species actually are really good at giving away electrons. For example, lithium, right? Lithium is a weak, low electron count metal. That dude gives away electrons like crazy. And you've probably heard of lithium-ion batteries. That's why. And the chemistry is fascinating. But the answer to your thought is no. These things don't have to be in contact to make this happen. They actually are in contact because all contact does is allows for an exchange of electrons. And that exchange of electrons can happen through a wire. And so that's what allows us to build batteries. Okay, because understand, and I love your questions, but we have to purpose together that we're not going to get fidgety when the bell rings. Okay, so we could talk about this all day, but we also have material we need to cover. So I'd love to chat, but the agreement is you're going to stay, and you're not going to get fidgety, and you're not going to pack up, because if you do, I'm going to kill you. So go ahead, Doug.
So a theoretical question, would a more electronegative cathode make it higher pressure?
That's a good question, and the answer is I have to think about it. Yes. Yes, it would. And that's actually where we're headed with this, because this is actually a measure of the pressures that these things are capable of generating. And we'll look in a second, because we're going to do one more. Go ahead. That's where we need to go next. So guys, here's the trick. Think about what's going to happen as this battery goes. So guys, as this battery goes, what's going to happen to the charge in this cell? It's going to become more and more what? Positive. And what's going to happen to the charge in this cell? It's going to become more and more negative. And guys, eventually, very quickly, what happens is we end up with this battery getting backed up on itself. So anytime there's a flow, that flow has to come full circle. And that's what the salt bridge does, is it allows for electrons to flow this way, but a similar flow of charge the other way, maintaining balance and completing the circuit. So guys, in this particular example, and those don't balance, but that's fine, an acceptable electrolyte in the salt bridge. So what happens, guys, is this salt bridge is actually full of an electrolytic solution. And what that solution does is it actually allows for the complete cycle to happen. So this is the way that I think about it. So we have negative electrons flowing this way, right? So if the negative electrons are flowing this way, to complete the circuit, the negatives have got to continue to flow like that, meaning that the sulfates will flow this way and the sodiums will flow this way, maintaining charge balance. Now, why did we choose sodium sulfate? Well, that's a common ion with the stuff that's in the cells, and sodium is a worthless conjugate acid. So it's a safe choice because it's not going to do chemistry in the cells. But again, guys, what happens is this salt bridge allows other charged things to migrate, maintaining charge balance, allowing for this battery to continue to flow and not back up. Yeah. It does. It absolutely does. Yeah. It can. And so understand that there's lots of things that happen when batteries die. And we're going to talk about those things next time. Yeah. You guys okay? Okay. So look at what we've got. We've got direction of flow, anode, cathode, oxidation, reduction. What's happening to the masses at each one of those electrodes? Are we settled with this? Okay, one more thing to talk about. Guys, they threw out this number, 1.10 volts. Where did that number come from? But first of all, let's talk about this. What does it represent? What do you know about volts? Pressure. Now, guys, join me in this concept, and I'm going to clean up my mess. Zinc ion, copper ion. So, guys, this is going this way, and this is going this way. And when we do, the current goes this way, and it's 1.10 volts. So, guys, what is creating that pressure? And I don't ask this rhetorically. What is creating this pressure? And this is to Luke's question a second ago. What's creating the pressure? Zinc atom giving away electrons and copper ion taking in electrons. So guys, zinc ion has a characteristic property that it wants to donate electrons. It's a big fat metal. It wants to give its electrons away. And it does that, ready? It does that with a pressure, a voltage. Guys, copper ion, on the other hand, wants to take in electrons. It has an affinity for electrons that allows copper ion to pull in electrons. And so, guys, literally what we've got going on here is this. Zinc atom is going and it's pushing out electrons. And copper ion is going and it's pulling in electrons. And that push and pulling together result in a voltage of 1.10 volts. Let's talk about where those numbers come from. So guys, what is this? Zinc is becoming zinc ion and electrons. Copper ion is becoming. It's what? Oh. Oh no, you didn't. Oh, you're so kind. Thank you. This makes me so happy. So guys, copper ion is gaining those electrons and is becoming copper metal. So where does the 1.10 volts come from? Guys, grab this table. Grab it with me. Find them. Guys, find these two half reactions on this table. Do you see it? Let's find the copper ones up the page, right? Or zinc? No, copper. Copper. So guys, note that you're given three different copper reactions. Which one are we talking about? The second one. Copper 2 plus ion plus 2 electrons yields copper atom. And guys, you'll notice that this happens with a voltage of plus 34 volts. You see it? So guys, notice the title. This is a reduction potential chart. This is a reduction. Are you okay with that? Guys, don't just nod. Make sure. This is a reduction. This tells us that copper ion pulls in electrons with a voltage of 0.34 volts. Now find zinc. See it down there? Guys, notice what this says. This is a reduction potential chart. So all of these half reactions are written as reductions. So we've got zinc ion plus 2 electrons yielding zinc metal, right? Now what is the voltage of that? Negative 0.76 volts. But guys, here's the trick. Watch close. Does this match what's on the table? No. What is it? The opposite. Because guys, this is not the cell where the reduction happens. This is the cell where the oxidation happens. So how do we turn oxidation into reduction? Flip them over. But what do you suppose that does to the voltage? Flips the sign. And now guys, you want to guess what you get when you add up 0.76 and 0.34? 1.10 volts. Let me keep going for a minute. So guys, the question then becomes this. We started this entire that the electrons flow in this direction. This was the idea. If the electrons flow in this direction, that makes this the oxidation, and that makes this the reduction. But what if we had never seen this before? What if the only thing that we had was this? How do we know that this is going to be the reduction and this is going to be the oxidation if all we have is this data? The one with the higher reduction, and they could both be negative, or they could both be positive. But the one with the higher reduction potential will be the reduction cell. Let me keep going, Mark. So guys, does that make sense? The one with the higher reduction potential will be the reduction cell. But now guys, this. What do we then need to do with those numbers to figure out the voltage of the cell? We've got to go over here to the oxidation cell and do what? Change the sign and then add them together. Guys, that brings us to an equation that you need to write down. And guys, the equation, I want to make sure I give it to you in exactly the right form. Guys, the equation goes like this. Guys, it goes like this. The voltage, write this down with me, the voltage of the cell is equal to the reduction potential, which is written like this, at the cathode minus the standard reduction potential at the anode. And guys, if you're paying close attention, this equation does the math that we talked about. So these are the standard reduction potentials. That's what this stands for. E naught subreduction is the standard reduction potential. But guys, what do we do with these numbers to come up with the voltage of the cell? How did we get to 1.10 volts? What do we have to do to this? Change the sign, because this is not reduction, it's oxidation, and that's what this does. Subtracting it mathematically changes the sign, and then you're just adding them together. Minus and negative is a positive. So it's cathode minus anode. The reason we're subtracting the anode is because that's actually not a reduction, it's an oxidation, so we flip the sign and add. You get the ideas? Okay, so Mark, you had a question. We okay? Guys, other thoughts or concerns or things you want to talk about? You okay? Okay, so guys, with that said, there is one more thing we need to talk about. This is no longer on the AP test. It used to be that in that AP equation packet that I would give my students, there was a standard reduction potential chart. They have taken that away. It doesn't mean you're not going to be solving these problems, but what it does mean is they will give you the reduction potentials that you need. They won't ask you to dig them out of a chart. Does that make sense? Okay. So guys, with that said, you guys learned so much today. There's a summary. Oh gosh. And here, guys, is your homework.